It burns in our sky every day, seemingly unchanging, familiar, and ever-present. But behind that daily brilliance lies one of the most complex and dynamic objects in our solar system. The Sun, our life-giving star, is not just a ball of fire. It's a vast, energetic engine full of mysteries we've only recently begun to understand. For thousands of years, civilizations built myths around its light and warmth, unaware of the immense forces at play within and around it. Today, thanks to cutting-edge instruments and advanced observational techniques, we can look beyond visible light and peer into the Sun's deeper layers, into wavelengths that were once beyond human reach. This journey takes us far beyond what the naked eye can see. By examining the Sun across the full electromagnetic spectrum, from visible light to the extreme ultraviolet, we're able to uncover the incredible dynamics that shape its behavior. In this episode, we'll explore the Sun's layered structure and powerful activity, revealing what makes it one of the most fascinating and crucial objects in our solar neighborhood. The sunlight we see may feel immediate, but it's anything but instant. What reaches your eyes or your skin was actually set in motion thousands of years ago. Deep within the Sun's core, where nuclear fusion creates unimaginable energy, photons are born. But escaping the dense interior of the Sun isn't easy. Those particles of light can spend anywhere from 10,000 to 170,000 years slowly bouncing their way out through the radiative and convective zones before finally emerging at the surface. From there, they travel the final 150 million kilometers to Earth in just over 8 minutes. By the time sunlight warms your face, it's already incredibly old. Seeing beyond the visible. The human eye is limited to a tiny slice of the electromagnetic spectrum, visible light. But the Sun doesn't limit itself to that narrow band. It emits energy across the full range, including ultraviolet, infrared, X-rays, and more. Observing the Sun in these various wavelengths opens up an entirely new view of its complex behavior. Ultraviolet and extreme ultraviolet imaging, for example, reveal phenomena that would otherwise remain invisible, like solar flares or intricate magnetic loops. This multispectral approach is essential for understanding how the Sun interacts with Earth, from triggering auroras to sending solar storms that can affect satellites, communications, and even power grids. The outermost layer of the Sun's atmosphere, the corona, is a region of extremely hot, thin plasma that stretches millions of kilometers into space. While normally hidden by the intense brightness of the Sun's surface, this ghostly halo becomes visible during a total solar eclipse, offering a fleeting glimpse of its true shape. But modern science doesn't have to wait for eclipses. Thanks to space-based missions like NASA's Solar Dynamics Observatory, SDO, we can now observe the corona in astonishing detail every day. Using extreme ultraviolet imaging, particularly around the 19.3 nanometer wavelength, which corresponds to temperatures near 1,000,000 Kelvin, scientists are able to study the corona's fine structures, track magnetic loops, and monitor its ever-changing activity. Beneath the corona lies a turbulent environment of magnetic activity. Among the most powerful events are solar flares, massive bursts of radiation that erupt when magnetic field lines twist, tangle, and suddenly snap into new configurations. This magnetic reconnection releases an enormous amount of energy, sending radiation surging across the solar system. These flares are more than just fascinating, they're influential. On Earth, they can interfere with satellites, GPS systems, and even cause disruptions in power grids. By observing flares in the ultraviolet part of the spectrum, researchers can track their development in real time, helping to predict their potential impact on our planet. Another key feature of the Sun's outer atmosphere is the presence of coronal holes, darker, cooler regions where the Sun's magnetic field opens up and allows solar wind to escape. These areas are less dense than the surrounding plasma and serve as high-speed channels for streams of charged particles. As the solar wind flows outward through these openings, it interacts with planetary magnetic fields and can have significant effects on space weather. When streams of solar wind collide with Earth's magnetic field, they do more than stir up space weather. They paint the sky. These interactions generate the auroras, vibrant curtains of green, red, and purple light that shimmer across the polar regions. Through extreme ultraviolet imaging, scientists can detect and map the origin of these solar winds, coronal holes, gaining a deeper understanding of how these dark regions influence the space environment around our planet. And thanks to Parker Solar Probe's historic flybys, scientists have now mapped the heliospheric current sheet, a massive spiraling structure of solar magnetic fields that stretches across the entire solar system. This magnetic ripple influences how solar wind moves and interacts with planetary environments, including our own towering above the solar surface, arcs of glowing plasma called prominences, or when seen against the sun's face, filaments, snake their way through the corona. These structures, suspended by magnetic forces, can extend for hundreds of thousands of kilometers, easily eclipsing the size of Earth. Some of these loops rise and fall in a matter of hours, while others persist for weeks or even months. Witnessing a prominence rise from the photosphere and bend gracefully through the outer layers of the atmosphere showcases the immense scale and raw magnetic energy of our star. In time-lapse footage, these looping forms appear to writhe and surge, revealing the sun's power in motion. Before we continue, if you're enjoying the video, a quick like would be truly appreciated. Not all solar material launched into the corona continues its journey into space. In some cases, plasma cools down, becomes denser, and falls back toward the sun in dazzling arcs known as coronal rain. This phenomenon, though seemingly delicate, involves plasma still measuring in the millions of degrees, too hot to exist naturally anywhere on Earth, yet gracefully flowing back along magnetic field lines to the surface. Recent advances in ground-based telescopes using coronal adaptive optics have revealed coronal rain in stunning detail. For the first time, scientists are seeing fine threads of plasma just 20 kilometers wide, gracefully cascading back toward the surface, offering unprecedented clarity into this delicate but powerful process. Occasionally, the sun releases something far more powerful, a coronal mass ejection, or CME. These events occur when tightly wound magnetic field lines suddenly snap and unleash a surge of energy, hurling billions of tons of charged particles into space. If one of these eruptions is aimed toward Earth, the consequences can be serious, disrupting communications, GPS systems, and power infrastructure. CMEs tend to happen during peaks in the sun's 11-year solar cycle. Thanks to observations in the extreme ultraviolet, scientists can track these outbursts as they form and travel, providing critical data for forecasting space weather hazards. In a remarkable update, NASA's Parker Solar Probe completed its closest flyby in late 2024, skimming just 3.8 million miles above the sun's surface. During this record-breaking approach, it captured the first close-up images of interacting coronal mass ejections and magnetic switchbacks, twisting kinks in the solar wind's magnetic field. These findings are reshaping how scientists understand the solar system's most violent outbursts. Different wavelengths, different stories. One of the most valuable tools in solar research is the ability to observe the sun across multiple wavelengths at once. Each wavelength highlights plasma at a different temperature, revealing distinct aspects of solar activity. For instance, viewing the corona at 600,000 Kelvin reveals gentle loops and less active regions, while imaging at 2 million Kelvin brings out hotter, more energetic phenomena. Side-by-side comparisons of these wavelengths often reveal surprising complexity. What seems like a simple arc in one view may in fact be a tangled network of interacting structures in another. This layered perspective is essential for decoding the Sun's many mysteries. Sandwiched between the Sun's chromosphere and corona lies a razor-thin but critical layer known as the transition region. Although it spans only about 100 kilometers in thickness, the temperature here climbs steeply, from a relatively modest 8,000 Kelvin to a blistering 500,000 Kelvin. To put that into perspective, the hottest molten lava on Earth reaches around 1,443 Kelvin. Even the base of the transition region is several times hotter, while the upper boundary exceeds it more than 300 times over. Observations in ultraviolet wavelengths allow scientists to probe this region, unlocking clues about how energy is transferred and distributed through the solar atmosphere. Beneath the transition region lies the Chromosphere, a 1,700-kilometer thick zone teeming with motion. One of its most intriguing features are spicules, thin needle-like jets of plasma that erupt from the surface and shoot upward at staggering speeds, often reaching 100 kilometers per second. Spicules can grow to nearly 10,000 kilometers in height and have incredibly short lifespans, appearing and disappearing within minutes. For years, their origin baffled researchers. The mystery was finally cracked in 2017, when scientists identified the role of neutral particles, previously ignored, in helping these plasma jets overcome the Sun's intense magnetic fields and burst into the atmosphere. Until recently, spicules were seen as brief, chaotic jets. But in 2025, researchers confirmed they actually play a significant role in transporting energy and material into the corona, helping to sustain its extreme temperatures and dynamic behavior. The photosphere is the Sun's visible surface, the layer we see shining from Earth. Though it appears solid, this outer shell is anything but. It spans roughly 400 kilometers in thickness and is made entirely of plasma, the electrically charged state of matter that dominates the universe. Unlike solids, liquids, or gases, plasma consists of freely moving ions and electrons, making it highly responsive to magnetic fields. And while the Sun may look like a glowing disk in the sky, what we're actually seeing is the upper edge of a vast ocean of superheated plasma. This is the deepest layer we can observe directly, and it's the source of all sunlight that reaches Earth, powering our atmosphere, ecosystems, and technology. A close inspection of the photosphere reveals temporary blemishes, darkened regions known as sunspots. These spots are cooler than the surrounding surface, though still thousands of degrees hot, and form where intense magnetic activity suppresses convection, preventing heat from rising. Sunspots often cluster in active regions and are closely tied to solar flares. Observations across both visible and ultraviolet light reveal that flares frequently erupt from the same areas that sunspots occupy, underlining the strong connection between solar magnetism and energetic events. Beyond the sunspots, the photosphere teems with dynamic textures. It's covered in patterns called solar granules, cells of hot plasma roughly 1,000 kilometers wide. Each one marks the top of a convection current. Hot material rises from the Sun's interior, cools as it reaches the surface, then sinks back down in a continuous loop. These granules don't last long. Most survive just 20 minutes, but their movement is anything but gentle. Plasma within them flows at supersonic speeds, reaching over 7 kilometers per second, generating powerful waves that ripple across the Sun's surface. High-resolution imagery reveals these granules as a shifting, bubbling surface, evidence of the turbulent activity hidden just beneath the light we see. Peering deeper, what we still can't see. Despite remarkable advancements in solar imaging, there's a firm limit to how deep we can look. The photosphere represents the outermost layer accessible to direct observation. Everything beneath remains hidden, shielded by layers of intense heat and electromagnetic chaos that current technology can't yet penetrate. Still, our ability to study the Sun across multiple wavelengths has transformed what we do understand. We can now observe solar flares, prominences, coronal holes, and spicules in ways that would have been unthinkable just decades ago. These observations continue to reshape our perception of the Sun as a living, dynamic entity, far more active and unpredictable than once believed. Why it matters. The Sun's reach on Earth. The Sun is more than just a source of light. It's the primary driver of Earth's climate, the force behind our weather, and the reason life exists at all. But it also poses risks. Bursts of solar activity can interfere with satellites, communications, navigation systems, and even the power grids we rely on every day. That's why solar science isn't just academic, it's practical. By monitoring solar activity across the electromagnetic spectrum, scientists are building tools and models to forecast space weather, helping to protect the infrastructure that modern life depends on. While we're cautioned never to stare directly at the Sun, nature occasionally offers a rare exception. During a total solar eclipse, the Moon lines up perfectly with the Sun, blocking the blinding light of the photosphere and exposing the faint corona, a glowing halo that surrounds our star. These moments aren't just awe-inspiring, they're scientifically invaluable. Eclipses provide a unique opportunity to observe the Sun's atmosphere from Earth. If you ever plan to watch one, remember to wear proper protection. ISO-certified eclipse glasses are essential to avoid permanent eye damage. With the help of real-time data from missions like Parker and advanced Earth-based telescopes, scientists are now building better models to predict when solar storms might strike. These improvements are vital, not just for protecting satellites, but for safeguarding aviation, communication networks, and national power grids. As our tools and technology continue to evolve, so too does our ability to observe and understand the Sun. With every advance in space-based observatories and imaging techniques, we inch closer to unlocking deeper layers of its structure, peering further into regions that remain, for now, out of reach. One day, we may be able to look beneath the photosphere and witness the hidden mechanics that drive solar activity from within. Until then, the Sun remains an endless source of fascination, an ever-burning reminder of the extraordinary forces at play in our solar system. This journey to decode our star is far from complete. Each new mission, each new image, brings us closer not only to understanding the Sun, but to understanding the universe itself. And as we learn more, we're compelled to keep asking, what else lies beyond? What other wonders await discovery? The Sun is not just a glowing sphere in our sky, it is a living, breathing star. Beneath its steady light lies a world of complexity, a roiling surface of magnetic storms, plasma jets, and radiation bursts. It's a dynamic system, constantly changing and essential to life on Earth. Through the lens of the electromagnetic spectrum, we've been able to pull back the curtain and witness its layers in unprecedented detail. We've mapped the fiery corona, tracked solar flares, traced the flow of solar wind, and observed the rhythmic dance of granules across its surface. Each wavelength reveals a different face of the Sun, and with it, a deeper appreciation of the forces that shape our cosmic neighborhood. Yet for all we've uncovered, the Sun still holds secrets, some hidden in plain sight, others buried deep within. But that's the nature of exploration. The more we discover, the more questions we find. So the next time sunlight touches your skin, remember, you're feeling the energy of a star that has burned for billions of years, sending its light across time and space until, in that moment, it reaches you. A quiet, daily miracle made visible by the power of science. If you could observe the Sun in just one specific wavelength, X-rays, ultraviolet, infrared, or visible light, which would you choose and why? What do you think it might reveal? Share your thoughts in the comments. Curious about how China's lunar missions are uncovering the Moon's hidden treasures, like helium-3 and water, that could revolutionize space exploration? Click here to explore the groundbreaking discoveries from Chang'e 4, 5, and 6 and see what Yutu-2 found on the far side of the Moon. If you enjoyed this video, I'd greatly appreciate it if you'd give it a like and share it with your friends. Thanks for watching.